So I'll share my PPT. Let me know if it is visible.
Yeah, it's visible.
Okay. So good morning. Actually, yesterday we talked about challenges in electric vehicles. What were the opportunities where we can do our research work, areas related to that. Today, I'll talk more about design and development of infrastructure, basically EV infrastructure. So before that, we must know what are the EV infrastructure, basically. Okay. So I request you to note down your questions. In the end, we'll keep around 15 minutes for question answer session. So last class, I just review. We talk about why we need electric, then why we need electric vehicle infrastructure. We all aware about because in last class, if nobody, I mean, maybe some people may not be there. So in last class, I also talk about the challenges in terms of technical, in terms of infrastructure, in terms of policy, in terms of market. So one is why electric vehicles. Already I have explained clean alternative, cost saving, domestic energy independence, cheaper to run, cheaper to make, health benefits, like that. Then why we need electric vehicle infrastructure? Obviously, when number of electric vehicles will increase, we need a support system, we can say. Okay. So in that, I mean, the scenario is after March 30, 2023, three-wheelers sold in the country should be electric one. And after March 31st, 2025, it has been proposed that two-wheelers below the capacity of 150cc sold in the country should be electric. And already government has a plan to sell electric vehicles by 2030. So even in 2017, it was also planned that policy of selling at least 6-7 million electric vehicles in India by 2020. So those are the targets. Basically. By keeping all these things in our mind, we should think about EV infrastructure. Like, for example, I have a cycle, so I must need a charger. Okay, I need a charging point also. And if I have an electric vehicle, obviously I need a parking lot equipped with charging station, or maybe at a domestic side, charging stations should be there, or maybe commercial charging stations should be available. So in order to charge that vehicle. So first we'll talk about what is electric vehicle infrastructure, or then after that we'll talk how to develop it. Okay. In our laboratory, we have developed type 1, or you can say level 1 chargers. I'll discuss about level 1 only right now. I mean, from hardware point of view, I'll discuss level 1 chargers with all the hardwares, all the results. Since we have not gone to a level 2 and level 3, so I'll just introduce about that, but not so, won't discuss the results and all for a level 2, level 3 chargers. Okay. So already I have explained that motivation to embrace electric vehicles, domestic policy, global impact, and in fact, environment impact, energy independence. Because yesterday I gave, I mean, in detail about all these things, so I'm just skipping. Developing nations, they have their goals: low cost conventional vehicle support, urban air pollution, and even in East Asia, like country like this, Philippines, Brunei, Indonesia, Malaysia, all those countries are looking towards EV. So those under the developing countries, basically. Climate change already, all those things already I have discussed in my last class, last lecture. These are the basically survey of global initiative, basically what America is doing, what Europe is doing, what Asia is doing in the electric vehicles. So country wise, United States, Canada, I'll share those PPTs. They're more on theoretical type, basically. So I quickly want to switch over the hardware type. Okay. So United States, Canada, Mexico, Brazil, what exactly they are doing in terms of electric vehicles? Germany, France, UK, in Asia, China, India, Japan, what exactly They are doing. Even Japan has planned that 1 out of 5 will be an electric vehicles. So they have already allocated 106 billion yen for this purpose. India, obviously, they have a 20% of the retail electric vehicles, plus smaller subsidies for two-wheelers. Similarly, China offers around 9,000 USD in subsidies, $9,000 USD in subsidies, and around 9,000 billion subsidies. And even they are planning to invest around $15 billion to help domestic automakers. So each and every country, I mean, along the world, along the globe, if you see that either Americans, Canada, Mexico, Brazil, in Europe, on Asia, what exactly the activities are going on regarding electric vehicles. Further, now we'll talk about EV charging infrastructure. So global electric vehicle charging. So basically, this market size is expected to reach 72.5 billion by 2025, in rising the market growth of around 39%. That is basically combined annual growth rate during the forecast period. The electric vehicle charging infrastructure consists of two primary fields. One is charging facilities and charging devices. When we are saying charging infrastructure, it means charging facilities. For example, let's say you have a parking lot in your campus. So the parking lot, which can, I mean, we have a facility of charging. Okay, so that is comes under charging facilities. And charging devices, what exactly device you are using for charging point of, okay, that is devices. I'll show my cycle charger also. I think I have in my office itself. So later on, I'll show that what exactly the planning is and how we are charging. Opportunity, charging stations, fast charging station, and battery swapping stations can also be listed as a public charging equipment. I told you battery swapping. One battery is charged, another is drained out. You can go to the swapping station. Drained out battery you can hand over in exchange with a fully charged battery and keep it in your vehicle. So two batteries you have, one in operation, one is idle mode, just like that. So that swapping stations also come under the charging facilities or charging infrastructure. Growing sale of EVs are anticipated to drive the global market over the forecast period due to public initiative and support in terms of tax credit and profitable subsidies. So in this charging infrastructure, basically, see the global electric vehicle charging infrastructure market size expected to reach 72.5 billion by 2025, rising at a market growth rate of around 13%. So this is basically how, see, first of all, how the countries, different countries in the world, they are thinking about EVs. Already told you. Now, if they are thinking about EVs because of so many benefits and all, we need to create an infrastructure for that. So this is a projected annual growth. The cumulative annual growth rate is around 39%. That would be the market size for a EV infrastructure, or you can say the charging infrastructure basically. This is basically forecast. I mean, by 2025, how the things will move on. EV market size and forecast in India. Then electric vehicle infrastructure market, that is also you can see. The earlier one was basically EV market. Now this is a EV infrastructure market. Okay, obviously when electric vehicles are growing, number of people are having electric vehicles, and definitely they are thinking for the services, the infrastructure. Because in the last lecture I talk about the challenges regarding infrastructure. Okay, you can see the projection that how the infrastructure, once electric vehicles are increasing or people will adopt more and more electric vehicles, then this infrastructure will have the same fate, since we need a service. Further, types of basically chargers. So electric vehicle charging infrastructure by market, either slow charger or fast charger. Slow charger take around 12 hours. Fast charger generally take less time. And in fast category, lot of chargers are there. Electric vehicle charging infrastructure by infrastructure market by connector type. So yesterday also I talked about Sedamo charger. This is a one Sedamo. Japan, basically Europe people are using this. Combined charging system (CCS). Now, electric vehicle charging infrastructure market by application. So either commercial or residential. You have your own charging infrastructure, maybe in your house, that would come under the residential category. And if you are using a parking lot, that could be a public parking, maybe municipal parking, or maybe your institute parking, that would come under commercial infrastructure, charging infrastructure. Now, basically, what the charging ecosystem is. See this, you have electric vehicle, you have a charging station. So remote user monitoring, energy generation, grid monitoring, management of fleet, and vehicle service management. Basically, there's a kind of a cloud. Okay, we have a server, and we are monitoring each and everything. Let's say you have a fleet. Fleet means let's say you have a charging station, or you can say charging. There is a parking lot in which lot of vehicles are there, and those charging lot owners are providing charging stations or charging facilities. So this will come under management of fleets. Fleets of what? Fleets of cars, you can say. Okay. So ultimately, now what does it mean? Why management of fleet? Let's say my office timing is 9 to 5. Okay. So the fleet owner or the person who is managing this parking, see, whenever we go in the market, we have some parking, some person manage it. This is, sir, you park your vehicle here, then they charge something, they hand over you one slip for that particular money. So a kind of management in that parking system. Okay. Similarly, in a management of fleet in EV, basically your EV owner, your no, sorry, not EV owner, your fleet owner or the charging facility owner, that will take care of each and every vehicles. Even he take care for that when one vehicle is arriving, one driver is arriving, or when one vehicle is leaving, that also comes under that. So this user behavior is unpredictable. Can you please mute your mics? Can you please mute your mics? I'm getting some voices, so can you please mute? Biswajit Mohapatra, can you please mute your mic? So basically, this is an unpredictable user behavior. Means we don't know when one vehicle will come, when will one vehicle will go. So this is basically comes under management of fleet. Grid monitoring. Yesterday I talked about spinning reserve of bed energy. So when there is any frequency drop in some area, you can transfer that energy. That is basically vehicle to grid. Or this is one thing. Another thing is, whenever you are putting your vehicle into the charging mode, how it impact the grid. Okay, because when you are putting something in plug-in mode, obviously this is a kind of extra burden, or you can say extra load on the grid. Okay, so grid monitoring, how the frequency responding, how the frequency is going on. So many things. So one is grid monitoring in that. Okay, energy generation, that is also coming to the grid. So I mean, these are basically overall electric vehicle charging ecosystem. It is not just your electric vehicle and your charging station, but so many things are related with that. Remote user monitoring. So means with your mobile app, you can find out where the charging station or where the parking lot. Accordingly, you can go there nearby. Okay. Even when I was in UCL in 2014, UCLA, that is University of California, Los Angeles, they have a 212 charging station in the campus itself. So there was a one mobile app. In US, we have a flexible charging, flexible tariff plan. Their tariff plan is very frequently depending upon the demand and supply. So with the mobile app, you can ask your vehicle that my vehicle can go into charging once the per unit cost of the electricity is, let's say, 10 cent. Okay, and it can go into the discharging mode when my electricity prices are 10 cent or 15 cents. Means at higher price you can send back to the grid, at lower price you can charge the grid. So ultimately you can earn some money that will be credited to your account automatically. Okay, so this is a whole as a charging ecosystem. It is not just like your vehicle and a charging is charge or nothing. It's a whole as a ecosystem for that. So this is basically EV electric vehicle charging framework. This EVSE is nothing but electric vehicle service equipment. You can see that you have a charging station. Again, this is a connected to the. You have a smart grid. Basically, this is a smart grid. You are having wind, solar energy, and again this EVSE management. These are the basically EV chargers, power electronics converter that perform the necessary functions for charging a battery. I'll talk about detail about power electronics converters because we have developed few power electronics converter in lab. So these are the basically chargers. See, now you see that a lot of type of chargers are there. I also have one charger in my just a minute. I'll show you. If possible, I can show it from here. So the charges you are looking here basically they depend upon the type of, because here I have one charger. I mean that will be the possibility. You can see it, we developed it here in lab. So this is the point where we can say that plug-in point, and ultimately this is the box having a all power electronic circuitry, and this is the point just to plug it into the battery. Okay, so simply, so you can see we have a 1 2 3 4 5 chargers here, and another charger this is with me in my lab, in my office itself. So if you see from here, depending upon the size and rating of the battery, the charges are there depending on the levels. Level 1, level 2, level 3. Whatever I have shown you, that is basically level 1 charger. I use it for my cycle to charge. And here, this is the charger basically, this one, and I'm just using a 30 volt AC, and this 3-pin. I'm just connecting this 3-pin plug into any AC circuit, and simply this charger converts this AC into DC and ultimately charging my electric cycle. Okay. So ultimately, this is the simplest one, level 1. Okay, and you will find here level 1, level 2, level 3, depending upon the requirement and all. Because here the system is quite small, so I'm using level 1 charger for that. So these are the different chargers, on board, off board, both are here. Now moving further, electric vehicle supply equipment. These are basically a lot of manufacturers are there. So EVSE is a protocol to keep the user and electric car safe while charging. Means preventing current from flowing when charge is not connected to the car. Ensure that if a cable is not correctly inserted, power will not flow through it. Can also detect hardware fault, disconnecting the power and preventing bad damage, electric short or worse still fire. Okay, so basically this is the role of electric vehicle supply equipment. Whatever I have shown you, this is a simple charger, but with lot of protection and all. This is basically EVSE, which is used to safeguard user and electric car while charging. So this is basically, further target means how to meet the demand 2020 or 2030. So type of charger, already I've discussed yesterday, type of charger on board and off board. So you can see from here, on board, means charger is inside the vehicle on board, means charger is boarding in the vehicle. You can simply understand like this. Okay, so I try to find circuit so that it would be easy to understand what exactly we mean by the on board. Means on board means charger is boarding in the vehicle itself. Simple. I mean, just to remember. So you can see from here we have a single phase AC or supply, AC supply, control devices, cord, connector, and charger inside the vehicle and charging this battery. Then we have a motor control to run the motor, and ultimately we are running the vehicle. Off-board charger outside here. Okay, and everything circuitry. I mean, your battery, motor, controller, and motor is inside. So now you see, if you want to see it through the pictures, charger in off-board charger is outside. Okay, so just see this one, the third first. I mean, okay, you can see. So this charger, you can see that your charger is, I mean, here only. Okay, outside. That would be off-board charger, just like. Okay. Now, so I mean, I think, I hope it would make it clear what exactly the onboard and offboards are there. Now, recharging system, basically EV charging system. Already yesterday in one class, I mean, one lecture, I have discussed the complete diagram. This is just a line diagram for that. You have AC-DC converter with PFC, then DC-DC converter and charging the battery. So basically, what we have done work at this point. Basically, I mean, we have developed DC-DC converters to charge the battery. I mean, assuming that there is a DC grid type scenario, and we are already, I mean, we have eliminated this course, and simply what we are doing, that DC-DC converter and charging the battery. Okay, so that I'll explain you later on. So this is just a charging, I mean, how to recharge the battery, charge or recharge. Okay. So if we talk about type of charging, conductive charging and wireless charging. Conductive, basically AC as well as DC. In this, labels are also defined, level 1, level 2, level 3, like that. In DC, we have a fast charger, DC fast charger, and another is wireless charger. So I'll explain the hardware part for both conductive as well as wireless charging, because we have developed hardware for both in our lab. Conductive charging, already told, AC chargers and DC chargers. So in this, basically level 1 charger and level 2 charger. So AC charging is carried out using AC charger, because whatever I have shown you earlier, that is also AC charger, because I am putting it into the AC plug. Okay, single phase already. I mean, single phase, 230 volt, single phase. So based on various level on features, basically we have a level 1, level 2, and level 3 chargers. So in level 1, it provides charging through 120 volt or 230 volt. Refers to the use of standard, basically 120 and 240 in terms of those US standard I'm talking about. Okay, in India this is 230 volt, and 230 volt single phase AC. In the US they have a 120 volt as a single phase. So refer to the use of standard household outlet, generally take around 8 to 12 hours. I told you that one e-rickshaw charger who are running e-rickshaws in the daytime, they overnight they charge it. Okay, level 2 charge, because we have, whatever we have developed, only level 1, because starting from 500 to 1 kilowatt chargers we have developed in our lab. So this portion we have done in our lab till now, since we have a funding project funded from DST. We have a one patent also in that, and those chargers we have developed that I will discuss. In level 2 chargers, if there's basically three phase, so 240 volt as per the US standard, but if you talk about India, so this is a 415 volt or 440 volt. It takes around 4 to 6 hours to completely charge. DC charging. DC charging carried out using DC chargers. It utilizes dedicated DC electric vehicle supply equipment to provide energy from appropriate off-board chargers to electric vehicle either in private or public location. So charge through 480 volt DC, known as a fast charger. Ratings are 50 kilowatt up to. Battery can charge in 20 minutes from the drained out to 80% as a full. So you also aware about once 80% is cross that I mean charging is a little bit slow. That the current flow which depend upon the energy conservation and current flow. So DC charger after this charger, this is basically the comparison between all possible charging levels. Level 1, you can see the maximum voltage available, maximum current available, and maximum power available. In level 1 charger, maximum current is 16 ampere single phase. So you can see that in level 2 charger 80 ampere. So means increase the value of current and ultimately you will get the charging time reduced. Okay, so in level 2 already we have discussed 240 ampere current. In level 3 100 ampere current. So you have to manage that current. So that's why I mean since laboratory has some restrictions, so we just reached to level 1 only because having a 16 ampere is fine in lab, but 80 ampere and 100 ampere this is not possible. So in the future we are looking to collaborate with some industry so that idea will be ours and our student can work in that industry. That's the pipeline. Already we are doing this in one another project that is related with electrical, that is related with solar. But ultimately you can see the level of current. If you come to the DC level, 80 ampere, then 200 ampere, then 400 ampere. So I mean, this is not practically possible to about current level. So further, this is vehicle charging stations and market share basically growth, how it will propagate or how it will forecast in terms of charging station market share, just like modes of charging. Mode 1 of charging. This is the simplest one, AC charging, because whatever means circuit I have told you, I could have included in my slide. But okay, live I'm showing you. This is basically this modes 1 charging is just like this only. This is your charger, and ultimately you are putting this AC plug, okay, and this is your connector in to charge the battery. So 250 volt single phase or 448 three phase of 16 ampere doesn't have extra control pins and protection, because whatever you have, this is inside this box only, your heat sink circuitry or that small protection or whatever. Okay, this is a SMPS inside, and this is a basically cooling purpose, this is there. So everything is there. I mean, you need not an extra communication and control pin for the protection and all. So this is just to charge the cycle or bike or maybe the lower one. I mean, at higher level also available, but just level 1. Then further, mode of charging level 2. In this, you need a communication control and communication circuit. Okay, you need extra communication control. Why this is come under basically EVSE? Why you need EVSE? Just to have a safety for the user as well as the equipment. Maximum current could be 32 amp. Here again, the difference between this and this, you can see AC charger, and then this is a fixed basically here. Fixed EVSE 250 volt single phase, 480 volt three phase, maximum current around 250 ampere. And this is further mode 4, AC to DC. Ultimately, you need a DC. So AC to DC conversion, and then ultimately you have a 600 volt DC including earth control highlight the maximum current of 400 ampere. This is expensive. I'll talk about, okay, wireless charging. So in this you have one transmitter coil and another receiving coil. So your transmitter coil may be on the road and receiver coil on the bottom of the vehicle. So the distance you need to keep, in our lab we have kept around 270 mm, or you can say 27 centimeter. Up to this distance, I think the ground clearance all the vehicles available, I think 30 centimeters, I think, okay. So I'll discuss in detail about this circuit also. So this is basically wireless. So that can be, I mean, this wireless type of charging can uh, that could be electric highways and all, we can use this wireless charging. So in the next slide, I think I have included this, so I'll let you. So again, this grid to vehicle to grid, yesterday I have explained that when you charge it, when you charge your vehicle, this is from grid to vehicle, G2V. When you discharge it back to the grid, this is vehicle to grid. So this is basically wireless charging. Now you can see we have a circuit, okay, power supply, transformer, rectifier, inverter, whatever we have. We have a coil. These are the means the coils which are here. These are the basically transmitter coil, and this is on the road side, okay. And this is basically pickup coil, or you can say the receiver coil. This black coil, this one. This is basically your receiver. So the way your vehicle move, we have a static as well as dynamic. Means once you stop, your charging will happen. Once you run also, or once you move also, then your at that same time also you will have a charging. Okay. So yesterday I was talking about this type of electric highways. Further, this you can see static, park, charge and go. That could be your parking lot, or that could be your bus stop at 2 kilometer. I mean, let's say in city when you are moving. So I think out 1 kilometer or 2 kilometer, every time you have a stop. So at that stop also you can charge it. So that is static charging, park, charge and go. Dynamic basically charge on the go. I mean, while moving itself you can charge. Now, high grid charging means you have a not only grid, you have, let's say, solar and your wind also. Okay. So grid is also there. You have a solar also, and either grid to vehicle or vehicle to grid. That's basically hybrid charging, recharging. Now, those are the basically connectors. I talk about in the present charger which I have in my lab. So here you can see you just know the laptop charger, laptop pin. Similarly, I have this pin charger right now for cycle, but that is called basically connector. This one is called basically connector. So if you talk about the type of connector, because here for a level 1 charger connectors are different. Okay, here you can see 3 connector. Yeah, we simply know about. Okay, commando, type 1, type 2. These are the AC connectors basically. 3 kilowatt single phase, 3 to 22 kilowatts, one single phase or 3 phase, 3 to 7 kilowatts. So these are the basically standard VS1363. Every vehicle need to have onboard charger, and this is basically your IEC 60309 SAE J1772, and this is basically DC connector. You have a Sedamo, you have a CCS, you have a Tesla. Okay, so these are the basically type of ones. Level 1 is fine, but once you move further for a high rating and level 2, level 3 DC charges, so these types of connectors are used. So you can see in SAE J117, this is basically protocol. Type-in connector mainly used in America and Japan. Then this is IEC 62196. So mainly used in Europe. So ultimately, the purposes of using this number of things and all, I told you that the safety EV, this comes under EVSE, electric vehicle service equipment, and the purpose is basically the safety of owner as well as the vehicles. I mean, there should be no extra current, no fire and all while charging and all. So that's why the safeties are there. L1, L2, L3 is nothing but your line 1, line 2, line 3, N is neutral, and other circuitry basically for the protection point of view. DC connectors, you can see that because for my cycle, whatever I'm using, that is simple a pin type connector, the same you are using in your laptop. But when you move further for combined charging system and DC connectors, the complexity increases. So this is basically Tesla charger. Which connector India is using? So I mean, simply this one you can talk about the 3-pin charge is available here. US, Japan, and now China is also competing with different type of chargers. So this is one pin, second pin, and now this is, I mean, just like your triple plug earthing and that. Further you move, EV charging station. So I'm talking about this type of charging station. It's just like your refilling station, okay? Roadside. Charging stations are inevitable, a part of electric vehicle ecosystem, because without charging station you cannot do nothing. In case India, we have a road network of around 5 lakh 47,000, I mean 5 crore 47 lakh 2001 kilometers. The continued nationwide network of charging stations for electric vehicles. So since government is planning to sell only electric vehicles by 2030, so we need charging stations, just like petrol pump or refilling stations. We need a charging stations. Are the basically solar powered charging stations. So this is basically comes under hybrid category. Already I have shown the circuit for that. This is something one we are planning to have in. Now comes to the hardware part basically. I'm getting some voice from the audience side basically. So I request you to mute. Can all of you mute your mics, please? Can you please mute your mic? Sandeep and Namarjit Ray, can you please mute your mic? So after the solar power, basically now I'll talk about what exactly we are doing. This is basically a smart energy and sustainable research lab we have set up at MNIT Jaipur. So in this lab, we have a few funded projects on electric vehicles. First one is basically one project on cooperative isolated renewable energy system for enhancing the reliability of power in rural areas. We are developing a microgrid in a rural area that is basically 16 kilometers from MNIT Jaipur, a village. Uh, the village have a grid, they have electricity, but the electricity availability is hardly 2 to 3 or 4 hours. So we are planning a microgrid there. That is not a actual microgrid, just like this is not just like a developing solar something there. But what we are doing, we are giving, we are using it as a grid. So whatever the functions of the grid are there, that we are achieving through the battery in this project. This is a 3 crore project funded by the DST. And project in this lab is basically development of various unidirectional and bidirectional EV chargers. So in this project, basically we are developing level 1 chargers starting from 250 watt to 1 kilowatt. We have developed few chargers. We have patented out of that. We have filed some patent also. So this project already finished, and we have developed few chargers in that range. So another grant we have for Spark funding, that is basically just to have a mutual collaboration with foreign universities. We have a collaboration with the University of Concordia. We have a collaboration with the University of New South Wales, Australia. Our student can visit under this grant, and their student, their faculty can visit to our lab in this grant. It's a mutual publishing, writing book, and doing research basically. So apart from these projects, one more project we in waiting that will also we'll get. That is basically on the solar inverter basically. So now under the one project regarding electric vehicles, since I'm talking for electric vehicles, so I'll discuss about electric vehicle project only. So in the funded project on electric vehicles, charger development basically, we are developing unidirectional charger. Unidirectional means grid to vehicle, just charging. Okay. Another is bi-directional, means we are charging from the grid and again discharging it back to the grid. Okay. So third one, wireless power transfer. So that hardware also we have developed in our lab. So basically, what are the requirement of a charger? I'm talking about basically electric vehicle design and development of EV infrastructure. So what are the requirement of a charger? So if you see, I mean broadly, we need a charger which is efficient, low cost and weight, efficient, low cost and weight, and size, reduced size. Means low cost, low weight, and reduced size, and another one is efficiency. So these are the four main parameters we are talking about the charger development. Okay. So out of these parameters, basically, what exactly we are doing here, how to make the charger efficient, first thing. So we need to think about what are the components in a charger or what new we can develop so that efficiency is high. If efficiency is high, same time we need to think about the reduction of the size, weight also. Since one company, this charger manufacturer, they contacted us basically. They have a one charger of 1 kilowatt, and the weight was 3 kg. And the efficiency was around 70% or something. So they told us if you can reduce the size and increase the efficiency up to 90%. So we did something. What we did, I'll let you know now. So what we did, we reduced the weight from 3 kg to 1 kg, and efficiency was around 95%. Now, how we achieve that? That is basically I need to discuss with you. So those are the general things, I mean not general, but you need to think how to achieve it. That reduce the weight, but how you will reduce that? I told increase the efficiency. What you will do to increase this efficiency? Okay, that need to think. So under this, basically, okay, these are the few projects in our lab. Some consultancy projects are also there. Just come to this one. So this is basically the chargers level. I mean, if you see, this is a level 1 charger, 1.8 kilowatt one. Already I have explained these are the current and this one. So in laboratory, we have developed to this one only. By that time, our funding is over, and we could have developed this one. So next target, we'll think to move further, and we'll write a few more projects, and let's see. So here, first, I mean, I've already pointed out what we are looking for in a charger. Okay, how to achieve that? Already I mentioned that we have developed this range of the chargers. So if you see the electric vehicles on board of a charger, so these are the basically standards. Already I have discussed in slides. Now, if we move further, in a charger, ultimately we are doing a rectification, AC to DC, then DC to DC, and the battery. Okay. Now, we are working mainly on this side, DC to DC converters, to charge the electric vehicles or battery. So the requirement for this DC-DC converter: high power density, high efficiency, high reliability, and economy. I mean, ultimately, all those things which I have mentioned earlier, we need to achieve here. How to reduce the size or increase the efficiency? First of all, if you decrease the losses, we can increase the efficiency. Now, how you will decrease the losses? First point. Generally, how we select the device? You know that MOSFET, low power rating, high frequency, IGBT, low frequency and high power rating. That kind of scenario is there. But if you, let's say you are selecting your MOSFET for some purpose, some application, then lot of type of MOSFETs are available. Okay, let's say I need a MOSFET for a 50 ampere and 500 volt. So in that range, a lot of MOSFETs are available. IRP 460, PX pin 1136, many others. Okay. Now which one you will select? Means all three are there. Cost may be different. Their cost may be different. But how to select that switch? You can't just have any switch. Okay. In the same range, more than 3, 4, 5 type of MOSFETs are available. More than that. Which one you select? You can select anyone. No, not like that. Okay. So if you see the data sheet of all those MOSFET, you see the Arun resistance. So that is basically responsible for losses. Okay. So I'll show you later on that one MOSFET is cost around 400, one MOSFET costs around 800, one MOSFET costs around 1800. Which one you will select now? It may possible that the MOSFET which is having a 800 cost may give more efficiency than the comparison of the 1800 rupees or 400 rupees. Okay. So need to check the data sheet and then purchase. And same time you have to trade off between cost also. So this is how we select the device. Now see, one term is soft switching. In power electronics, these are the general voltage and current characteristics, I and U. In power electronics, we always operate, or we should operate, we must operate our switch either in this cutoff region. You can see this one. This is basically the cutoff region. Below this, the linings are there. Either we operate our switch in this region, this cutoff region, basically this one, in this region. Okay. This red marked region, we should operate our switch in this region. So here if you see in this region, your current is ideally zero. I'm saying ideally, okay? Your current is ideally zero. And if you operate your switch, I mean, here in this region, basically this region, I will say cutoff region, basically sorry, cutoff, and this is your linear. So either we operate in cutoff region or linear region, but never in saturation. Okay, never in saturation region. Either in quasi saturation, you can, I mean, from here to here, quasi saturation, when your saturation is just to begin. Your saturation is just to begin. So ultimately, either operate your switch in cutoff region or this linear region, or maybe quasi saturation when saturation just to begin. Okay, but never in this region, never in saturation region, never, because when operating your switch here, you have a value of current and voltage, P equals to V into I. So power losses will be very high. So in power electronics, your switch must operate in this either cutoff or in this linear region to have a ideally power losses zero. See here in cutoff region, your ideal current is zero. So P equals to V into I. So ideally power losses are zero. Here, your ideally your power, I mean your voltage is zero ideally. So ideally your power losses are zero when you are operating your switch in cutoff region or in linear region. Okay, so we must operate our switch either in cutoff or linear region. So once you have this type of, I mean, this is called basically zero current switching. In cutoff region you have a zero current switching, because here you have a almost zero current. Here if you are operating in this linear region you have a zero voltage switching, ZVS. So either operate ZCS or ZVS. Okay, if you are operating in a saturation region, if you are operating in a saturation region, you can see these are the losses basically. This is the losses, power losses available. So because of these, you have a low efficiency because these are the your switching losses. Okay, and if you operate here in a zero current and zero voltage, you see your losses are negligible, or I mean ideally zero, I would say. Okay, so first of all, soft switching. We must operate switch in such a manner that we must get a soft switching. But to achieve soft switching is not so easy. I mean, people have achieved this soft switching and at a higher load, or you can say uh, heavy load. Okay, but at a lighter load, this soft switching get lost. Okay, so in many of the reported work earlier, basically they are not able to soft switching. They have a soft switching at a particular instant, but not all the operating range. I mean, starting from low load to high load, soft switching was not available. High load it was available, but not at the low load. So we achieved this. We achieved it by with the help of a PWM strategy. We achieved it by having some modification in the circuit. Ultimately, we achieved it, and with the help of this, we are able to increase the efficiency of the converter and ultimately the efficiency of the charger. This is one thing. So basically here, I mean, in this circuit, I understand, I mean, understanding at an instant and even in an online mode is not so easy, but I'll try my best to make you understand what we did. This was the earlier circuit, and this shaded portion, this portion we added in that just as a modification in the circuit. Because what happened earlier, at a light load, this coil got de-energized and soft switching lost. So now what we did, we modified the circuit, we name it something, and this is now our charger circuit basically to charge the battery. With the help of this, we are able to achieve soft switching at a load range starting from zero load to the full load. Okay, and once we achieve this soft switching, losses reduce. Once losses reduce, we are able to reduce the heat size. Once heat sink size is reduced, overall weight of the charger reduced, and efficiency is also increased. Okay, so this is basically how to select a switch. I told you earlier that three types of MOSFETs, four types of MOSFETs are available. And if you want to use MOSFET in your system, okay, which one you, so IRP 460, IXFN 64N60P, IPP 65, these are the name of the MOSFET. Different company, maybe some maybe Moser, maybe Fairchild, or I mean semiconductor, so many companies are there. Now you see the cost. The cost of IRP 460 is 300 rupees only. Cost of IXF64 and 60P is 1800 around. And IPP 65 are 45C7 cost around 820. So now which one you need to select? Some of you may be thinking that the 1800 would be better. The MOSFET which cost around 1800 would be better. But ultimately, when we did the analysis, found that the efficiency of the IPP 65 is, I mean, for a 1 kilowatt charger, it giving around 96.11% efficiency. This is around 1.5 more than the other one, and around 1% increase than the charger which cost around 1800. So need to think precisely uh, which switch we are using. Okay, even selection of switch itself can increase or decrease your efficiency. Okay, although you are using soft switching, this, that, blah blah, but if you have not used the proper switch, ultimately that can cost you the efficiency also. Okay, so now here we did a trade-off. Here we go for a higher efficiency. That higher efficiency we are getting in 800 rupees. So we go for that, and we did the analysis. We published this in a IT Power Electronics. Now further, these are the few circuits we developed in the laboratory. Starting from scratch, everything is done by my student only. Starting from PCB design to making this PCB in lab itself. All those chemical process and whatever, we did everything in lab. So here we did slight modification in the circuit to achieve soft switching. Once you achieve soft switching, losses reduces. Once losses reduce, heat sink side reduce, overall weight of the charger or the weight of the system reduce. Ultimately, we are able to charge this. So this is basically prototype for 500 kilowatt. With hardware implementation, we use a DSP TMS 320 F28370 as a basically platform in which we use this. Means this is not all about funding. This is not all about funding. This is basically this is a low cost. I mean, the cost of the DSP kit is around I think 7,000 or 8,000 only. And overall things, I mean, if you have a 20,000 to 25,000, you can develop a charger. Okay, this is basically laboratory type. When you go for a production point of view for this charger and all, the things would be different. Okay, the cost will be around 900 or 800. So because instead of using this, you can use just simply a programmed chip. Okay. Further, this is the soft switching we achieved. You can see here zero voltage switching. This is zero voltage switching here we have achieved. Whatever I have shown you earlier in the characteristics. So these are the basically analysis of the losses in each part. Turn on switches, turn off switches here. All the diodes, wherever. I mean, because we also modified the pulse. Earlier, we are using that phase shifted modulation (PSM). Instead of PSM, we use modified PWM. In a modified PWM, slightly we change the pulse width of the switches, and it gives us ultimate result. I mean, we have compared with the PSM with the MPWM, so I'll let you know how the efficiency increased. Okay, so not only selection of the switches, not only soft, the way you are giving pulses to the circuit, that also matters in order to increase the efficiency. Okay, is I have already discussed 4 ways change in the circuit. So by 4 way we can reduce the losses, increase the efficiency. Although also we can reduce the size. So you can see power distribution and loss on the proposed topology. So you can see that the power losses get reduced in compared to the other one. And further, this is basically the comparison what earlier people have done and what we did and how we are able to achieve the desired result. So you can see in this that the earlier one, here you can find no ZVS was there, and here we find, you can see that this is achieved, we have achieved this ZVS. So you see one thing, earlier in the same circuit when we are using phase shifted modulation, we are not able to get ZVS. When ZVS was not there, we have a losses. Okay, when we use PWM, modified PWM, we got ZVS. Got ZVS, reduce the switching losses, increase the overall efficiency of the system. Now further, the comparison of the losses. You can see the change in efficiency basically. When you have a PSM, phase shifted modulation, and when you have a MPWM. So you can see the increase in the efficiency. Around more than 2% increase in the efficiency. So when you are dealing with a big system, 2% matters. So this is how we are able to achieve the reduction in the losses and increase in the efficiency. Further, you can see, I mean, this is around 89% and 95%. So here you have a around 6% increase in the efficiency. So 6% increase in the efficiency is a huge. This is the charger which was given to us by some industry, that is Continental Power, somewhere in Uttarakhand. We reduced the weight to 3 kg. You can see a big heat sink is there. If you can see, a big heat sink is there inside this. This is because losses are high. Once you have a losses high, in order to dissipate those losses, you need a heat sink. Okay. So what we did, basically we modified this and we incorporate soft switching here, and we change the switches also. So once we incorporate soft switching and use PWM, then ultimately the loss is reduced and the size of the heatsink was also reduced. So this is some charger which is kept in our campus. This is deployed by the REAL, Rajasthan Electronics and Instrumentation Limited. Since we don't have any electric vehicle in our campus, we have only cycles and bikes which is made by our lab or our student. So we try to use them same up. Otherwise, I have a charger here itself, because charging station which is deployed by the REAL is outside. I mean, maybe some 300-400 meter away from my office. So when I have to charge in office, I simply use my charger which we have developed in lab. So further, these are the wide axis basically power flow. Basically, we are doing charging from the grid and discharging to the grid. Ultimately, this is basically DC to DC only. It means first we charge the battery, then taken back from the battery at a DC link. We have not sent, I mean, till now we have not sent back to the grid. Okay, we are working on that. Since low power, you can send it easily, but when you have a high power, you need a lot of communication protocols and all. So this is a combined work of computer science, electrical, electronics people. This is a one universal charger developed by MTech student who is right now, I mean, somewhere in Tripura. We published it in IT Power Electrons. So we can have a charging, discharging, propulsion mode, regenerative braking mode from this converter, this charger. All mode can work. And further coming to the wires, basically, this is a charger of around 600 watt developed by one of my PhD student. You can see here, you can see this is a converter basically here. Now the connections are coming to this coil. I mean this one, and this is basically the transmitter coil, one on the top one transmitter coil, and the below one is a receiver coil. So the distance between this transmitter and receiver coil is around 270 mm, or you can say 27 centimeter. Ultimately, the receiver coil, I'm taking this wire and we are charging this battery. This is basically battery pack. Lithium ion battery is there. So we are charging this. So this student already submitted the thesis, and we are waiting for the review. So this is something at laboratory level we did for wireless power transfer. And my students, actually, they have developed, they have incubated one startup. I'm mentor for those students basically. So this is basically they are developing electric cycles, electric bike and chargers. So basically what they have developed one cycle. That cycle is basically the speed is around 25 kilometer per hour maximum speed. Uh, in a single charge it go around 35 kilometers. A charger of the same cycle, actually I have shown you a number of time between my lecture. So even right now I'm using this cycle. They have made number of cycles and bikes, not bikes. Bikes only one they made, only single bike they made, but cycles they have made many cycles they have developed in different segments. So I generally used to charge it only once in a week or 10 days, and this is fine in campus. Yesterday also I talk about this cycle only. The motor which we have used, that is 36 volt 250 watt DC motor, that is basically hub motor. 10 ampere hour 36 volt lithium polymer battery we are using. It took around 2 hours to get fully charged. Already I have told you that this is a level 1 charger, and level 1 charger is taking extra time in order to charge. These are the basically cycles made by the student. This is basically fat tire bike. This is a cycle come bike, but ultimately the speed is 25 kilometer per hour maximum speed. This is the another one. So battery is, you can see between the triangle the battery is there. We went to one industry in Jaipur, and student worked with them as a courtesy to design this battery. So this is a specially designed battery for cycles only. So I'm using one of the cycle. Then further, this we also called e-bike. This is another segment of the cycle. You can see the battery here. This is a battery basically in between triangles. So two different type of models are there. This type of battery segment and another this type of battery segment. So that depend upon the people who like what. So this is basically nature friendly, reduce risk of. I mean, this is the advantage of riding a cycle. Okay, this is how we do some R&D involved, charger development and all. And this is testing, and ultimately these are the cycles which is, I mean, developed by the student. This is basically team. My students, they are working in this. I'm a mentor and advisor for them. This is basically 1 year back we did a test ride for this cycle. So ultimately, whatever charger we have developed, whatever cycles, e-cycles or bikes we have developed, one bike they developed earlier, and even the students sold out before incubating this startup. So I have not shown that bike here, but ultimately right now we are working to develop a bike that can run around 100 kilometer maximum speed, and that is basically we are trying to build that one. We are trying for funding also, that we can get some funding and we can work on that side. So ultimately target is whatever available in the market in the bike segment, we want to develop better than that. So these are the few publications from my lab. My students are working day and night. I mean, in the last year we got around 10 or 11 transactions. IIT, IEEE, like that. So this is, I think I should close it now. I should keep some more time for a question and answer also. So under this design and development of e-infrastructure, first thing which I told about, what are the basically, what is EV infrastructure, why we need EV infrastructure, what type of EV infrastructure could be developed, and what we have in level 1 charger. So whatever we have developed, that only I have discussed. Since I have not worked in level 2 or level 3, I could not discuss that. Maybe in the future, once we develop something in that side, I will definitely discuss and disclose with you people. So thank you from my side. Now I'm open to your questions. Please ask.
Sir, what is the typical frequency used in a wireless charger?
In wireless charger, basically what we are using, that is nothing air core transformer, you can say. Okay, this is a one transmitter coil, another is a receiver coil. So this is a kind of air core transformer. We are through induction only we are transferring the power. Okay, you can see in transformer those are not electrically connected, but those are magnetically connected. Okay, So this is a line frequency only, nothing else. But the frequency for the switching frequency of the converter, that is basically around we have 80 kilohertz. I think we run that on 80 kilohertz. The maximum frequency which we have achieved in lab is around 147 kilohertz. Even this is less only, since when I visited the University of Maryland, they have are working on 1 megahertz also. Okay, so we are on the lesser side only, but the maximum frequency switching frequency we have achieved, that is 147 kilohertz.
Yes, sir, in that battery operated cycle, it also have a pedal mode. So while
Which
changing
mode?
from pedal mode, I think it also allows the pedaling. Without battery, if you want to do the
Yes,
pedaling
yes,
and want to,
yes, yes, yes,
then
yes, correct.
whenever you are changing from pedal mode to battery mode, and again from battery mode to pedal mode,
Hmm.
whether there was any challenges, I mean, what type of
No, nothing,
challenges?
nothing, nothing,
Uh,
nothing. There's a one simple switch, okay, or you have to press it. That's all. Just when you have to start something, you have to press something, okay. So just press it. It will be in electric mode. So press it. It will be off. So it will be in a simple pedaling mode, okay. And you start pedaling, nothing else. This is your electric mode and your pedaling mode is separate from each other. Just to push
But
a button.
some kind of switching is required on a mechanical part, because you have to move from
Nothing,
motor
nothing.
to.
Nothing. This is quite simple. You just switch off the supply to the motor. Simple. And
Okay, okay.
when you are handling, handles are there. Now, when you put your hand on handles, nearby one small switch is there. You have to press that, not on and off. Press it simply. So once you press it, it will be connected in an electric mode. Again press it, it will be out of the electric mode. So ultimately the switch is basically a medium to supply power to the battery. You press it, supply will go to the battery. You have accelerator in your hand, you start accelerating, your motor will run, okay. And depending upon the acceleration, you can achieve the speed. Again second time you just switch it, I mean just press it again, it will be cut down from the electricity mode, or there will be no supply to the motor. Now you can use your pedaling. And I use it, I mean morning or even when I have to do pedaling with my son, so simply I use it in a pedaling mode only, because they don't
And
want.
during the pedal mode, does it charge the battery again?
This provision we have not kept till now, but as I've told you earlier, one of my students developed that universal charger. So with the help of that universal charger, the regenerative mode can also be incorporated in that. But right now, the present cycle, this is not there. Yes, but we can do that.
Okay, okay. Thank you for that.
Energy released that can be used to recharge the battery simply. Yes, please. Any other question? I think I should need to check in the chat box also.
How much these vehicles are safe, actually, electric vehicles? Because battery, is there any problem of battery blast or something like that
Yeah,
while
sir.
traveling? Yeah.
Yes, sir. Yes, sir. Sir, yesterday I talk about this battery. Basically, lithium-ion battery. You need to use a battery management system. Without battery management system (BMS), this is like a bomb. Okay. So when you are using unregulated charging or uncoordinated charging, definitely this is a, I mean, dangerous. So properly managed VMS you have to use in order to charge this battery. So in that case, this is safe. And one more thing I'll let you know, we are keeping this battery in the triangle area, either in a box mode or in a just to make it more glossy in a, I mean big mode, okay, or in a lucrative mode, you can say. So, but in when I visited this uh, uh, I visited in 2019 for this conference, US conference, Baltimore. So in Baltimore, I saw that they kept this battery on the backside carrier. Basically, in our Indian system, we have a carrier. Okay, so carrier on the carrier they kept this battery and wrapped it in a basically steel seat. Okay, that is more dangerous in comparison, because first thing is you can't sit. I mean, nobody can sit over that. One thing. Okay. Second thing is, uh, I think the safety. Okay. So somebody suggested me that why don't you keep this battery under the seat? So again the same question, the same issue, safety. Okay. So if you charge it properly, there is no issue of blast, because since I'm using this cycle since 1.5 years, and I think because we have not kept meter in this, but I think more than 3,000 4,000 kilometer it has run, around 5,000 kilometer it has run. The cycle has already run, complete the run. We have never faced any issue in that. Even 2 3 nights it was kept in the rain. I mean, by mistake I just park it outside my gate, and it was in a rain for 2 3 days in a rainy season last this year itself. Nothing was happened. Okay, and for the terrain point of view, we have a hills in the Jaipur, the fort which was made by the earlier king on the basically on a high terrain. So the cycle was comfortably running over that. Okay, so I think there is no issue in terms of that. There is, I mean, since 2 years I have faced nothing, but you have to take care for the BMS, battery management system. That's all.
Sir, in two-wheelers and cycle, it's okay, but for four-wheelers, like, its
Yes, sir.
battery size is very huge. So
Yes, sir.
in
Yes,
that
sir.
case,
Actually, that's why EVSE is there, electric vehicle service equipment. I told you in the mid of my lecture. Level 1 is fine. Okay, we are using and we are at level 1 right now from laboratory point of view. But when you are going for electric vehicle, so a lot of things are there. A lot of protocols are there. SAEG, J11, some set of protocols for DC chargers. So those protocols we have to use. Then that those protocols are basically for the safety point of view only. I have mentioned in one of my slides. If you use those protocols for higher levels, then there is no problem at all. Okay. So if you have any questions, please let me know, or should I go in the chat box? So I'm taking few questions from the chat box. Is all our static charges? No. I mean, you are referring to one of the slide. Both are there, static as well as dynamic. Any advantage over on-board charger than off-board charger? What about cost? Basically, when this is a on-board, so your body to weight ratio, that volume to weight ratio, that would increase. So ultimately, this is a, you can say, I mean, that is the only thing which I can, since your charger is also in the vehicle itself, so the overall body weight that would increase. That's all, nothing else. Safety point of view also you can think about. Why can't we manufacture some universal connector for AC/DC? We can. We need to work in that direction basically. Now, what is frequency used for wireless charger? Already I have told about this question, already answered. Does it have a dual mode, pedal mode and battery mode? This also answered. What type of converter you use in your cycle? That is DC-DC converter, basically AC-DC converter. First is AC-DC, then DC-DC. So this is a simply, first of all, we are converting AC into DC, then with the help of DC-DC converter, we are charging the battery. Then electrostatic or electromagnetic, which is having a more charging efficiency? That question I need to find out. Electrostatic and electromagnetic. I can't answer it properly. I need to find out this one. What exactly you are asking about? I think electromagnetic, we are using this electromagnetic only here. Okay. This is all about electromagnetic, which were right now we are using in our charger. Then further, is the dynamic charging reached the application level? This is basically not at application till now. Okay, but basically research development and some testing level is are going on, because whenever you are going for this wireless charger, so the position of your receiving coil and transmitter coil matters. Let's say your receiving coil is shifted by some angle or something, then again the scenario you need to think about. So static and dynamic charging play a role with respect to the position of the receiving coil. So, any other question from the audience side, please?
There is a question, is dynamic charging reached the application level?
I told you that dynamic charging basically this is in a basically application phase, not application level, basically not commercially available, you can say, but in laboratory type, people are working on that. I told you that you have a transmitter and receiver coil. So the transmitter coil is, let's say, fixed. Okay. So when your receiver coil is moving around or something, so there are charging issues. So how to charge in that case? So those all are going on. Even we have a submit one proposal when for this wireless charging itself regarding the dynamic when it moving dynamically, how to charge it and all. So not at application level, but this is basically the process further that we could see this technology mature in the coming years.
Question there is, what is the cost of your cycle?
Cycle basically single piece. This was around 22 to 25,000, I think. The main cost is battery and motor. Charger cost is nothing, hardly 1,000 or maybe 1,500 it will cost. The casing and all is available in the market itself, but the circuitry, if you produce in bulk, obviously this will be around 6 or 500, but single piece if you make, that will be around 1,500 or something. So 22 to 25,000. But for this case, you need not to wear helmet, you need not to have a registration, you need not to follow any RTO rules that is there.
There is a question in the
What-
chat box, if you can follow up. Few questions are there.
What is the amount of power charged when the receiver crosses the transmitter? Yes, correct. Basically, this is something I have not worked in this area simply because I kept one transmitter call and one receiver call. The position was not dynamic. This was a static. Okay. When you are going for a dynamic, then definitely the capacitance developed depend upon that how it will charge and all. So I have not done research in that area, but definitely the position effects. And for that itself, I have sent one proposal to DST. If we got funding, we will work in this direction. But definitely it will affect. And whatever we have developed, whatever we have done in lab, that is actually static, not dynamic at all. In cycle, if some issue with the battery after a few years, can it be used as a normal? Yeah, I told you now, this is just a push button. Push it will be in electric mode. Again, it will be in a without pedal mode. So this is your cycle only, which we are developing into electric cycle, simple. So you can use that. Even I am using in pedal mode, and whenever it required, I use in electric mode, simple. So both way you can use. Which one determine the life cycle of the battery? Basically, in your battery, we have around 3,000 cycle or 5,000 cycle like that. But definitely, your charging, discharging ultimately reduce the life of the battery. So yesterday itself, I discussed the efficiency and the driving range of the battery is an issue in order to adopt those electric vehicles. It is possible to use fuel cell in place of battery. Yes, we can think of, but not. I have not done it practically, but definitely we can think of if we can use this fuel cell. But can it storage the energy? I think of supercapacitor and all those things probably. But fuel cell is a kind of a solar cell or DC basically. Ultimately, again, instead of fuel cell, fuel cell is a kind of source. So again, you have to use battery for charging. Okay. So as a source you can use, as a source of electricity you can use. Similarly, the solar you are using to at a rooftop of the charging station. That's all. So any further queries from your side?
Any radiation issues comes during wireless charging? Someone has asked.
See, we have not measured any such type of thing, and I don't think radiation is a issue because this is just a air core transformer. We are not doing this communication level like a mobile tower and all, not like that. Okay? So we are just using a air core transformer, and this is basically induction, nothing else. Simple induction in a transformer. Instead of a magnetic core, we are just using a air core. So no radiation at all for this purpose.
Any more questions from anyone? You can post to Dr. Arun Kumar. Today is his last session, so I think if you have got any questions, you can post to him. And I think in future you can write to him in case of any further queries or something.
Yeah, I have my mail ID is there. Even my contact number is also there. So in case of any, real discussion, you can call also. But better to prefer mail also. But you can call also, but mail would be better. So I'll be available. I'll love to discuss the things which we are doing.
So any more questions or queries? If we are done with any more questions, anyone? So thank you, Dr. Arun, for your wonderful session.
Thank you, sir.
And enlighten
Thank you very
everyone.
much.
And
So my effort was to introduce what we have done, and I understand that in a online mode it is not possible to make each and everything understand in terms of hardware. So I try just to give the overview that what exactly we are doing. Okay, so let's see how people have
definitely, I
understood
think
that is.
this is just an energization software workshop, I can say, because in online we cannot go for the hardware-based or the laboratory-based things, or we can show those things also if we wish to, which is not possible. Again, interaction is a huge issue when we go for an online mode. Still, we are trying, as the situation goes, to have this type of modes. I hope you.
Sir, your voice is not coming. Okay, sir, thank you very much. Okay, no issue. There's some problem with voice. Okay, so I think I should leave now. It's fine. Bye. Okay, sir.
Hello, am I audible? Am I audible to all?
Yes, sir. Yes, sir. Now you are audible.
Yeah, there were some technical issues. So our next session will start from 12 p.m. as we mentioned in the schedule. I want to verify or recheck something with someone. Is Dr. Sudha out here? Dr. Gopal Sudha? I have dropped you an email also. Dr. Sudha Gopal, are you out there? I don't know whether she is able to hear me or not. Please reply me or call me up. Because actually, Dr. Sudha, I don't think she is there. Okay. So we can take a break for say 30 to 25 minutes, around 20-25 minutes. We can take a break. Again, we will assemble in online, of course, at 12 p.m. to start our next session. And I have gotten issues to Madam Mithu Sarkar. Is she there over here? Madam Mithu Sarkar, is she there over here? Can you unmute yourself if you are there?